Welcome to the video lecture series on engineering mechanics. As part of this course, today we will be starting the third unit, centroid and center of gravity. In this video lecture, we will be discussing the introduction to the center of gravity and centroid. The overview of this video, we are going to cover definition of centroid and center of gravity, and we will be deriving the analytical expression for finding the coordinates of centroid and center of gravity. Let us start with the definition of center of gravity and centroid. The center of gravity is the point where the total weight of the body is supposed to act. This is the point where the total gravitational force or the total weight of the body act for any orientation of the body. Look at this diagram. In the first figure, the body is suspended through point A, and G is the point center of gravity. And again, in the second image, the body is suspended through B, but the center of gravity is not changed. And again, in the third image, the body is suspended through the point C. Still, the center of gravity, the point is not changed. So, the centroid or center of gravity of the body is a constant point. It will not change with the orientation of the body. Center of gravity is also defined as a center of mass. Center of gravity, in the first definition we have seen with respect to weight, where the total weight of the body is concentrated, or the point through which the body is pulled towards the earth center. That is what center of gravity definition. Now, in the second definition of center of gravity, it is center of mass, the point where the whole mass is supposed to be concentrated. The total mass is supposed to be concentrated at one point. That point is called center of gravity. And in the third definition, we can see it is also the volume center. It is also the volume center. The center of gravity of a solid body is not only the point through which weight is being acted, or the point at which the total mass is supposed to be concentrated, or it is the center of volume of the body. Coming to the centroid is the geometrical center of plane objects, which are two-dimensional objects, like one-dimensional objects also, like line, curve, rectangle, triangle, circle, semicircle, parabola, parabolic spiral. All these are plane objects or plane figures or areas. The center of planes are 2D objects or 1D objects is called centroid, and the center of 3D objects or solids is called center of gravity. The centroid of a line and the centroid of an area we can calculate by using the formula which are going to be derived later. The centroid is the center of geometrical shape. Here the geometrical shape is triangle. Graphically we can find the centroid by drawing the medians. The intersection of all the three medians is centroid for the triangle. Now, in this video lecture series, in the coming videos, we are going to find the formula, analytical formula for finding the centroid of different shapes like rectangle, triangle, semicircle, quarter circle, etc. Let us see the derivation of general formula for finding the center of gravity and also the centroid. Consider a body of mass m and weight W and let G be the center of gravity through which the total weight of the body is supposed to act. Let xy be the reference axis for locating the coordinates of the center of gravity G of the given body, and x bar and y bar be the coordinates of the center of gravity of the body with respect to x and y. Let us look at the diagram. See, all these points are shown in the figure. The body of mass m and weight w, and g be the center of gravity through which the total weight capital W is being acted, and the x and y be the reference axis for locating the center of gravity of the given body, and x bar and y bar be the coordinates of the center of gravity with reference to the taken axis. See, x bar is the distance of the center of gravity from the origin measured along x axis, and y bar be the distance or coordinate of the y coordinate of the center of gravity measured along y axis. Now we are going to find the analytical formula for finding the center of gravity coordinates x bar and y bar. For that, let us divide the body into n number of parts whose weights are W1, W2, W3 and so on, and Wn. So the each and every part has its own weight. All the weights are acting in the downward direction, vertically downward direction. Now each and every part has its own center of gravity. The divided parts are having their own center of gravities, and the coordinates of the center of gravities of individual parts are x1, x2, x3 and so on, xn, and y1, y2, y3 and so on, yn. So each and every part has its own center of gravity, and the coordinates are given like this: x1, y1, x2, y2 and x3, y3. Now here the sum of all the weights is equal to the total weight. The sum of all the individual bodies, the sum of weights of all individual bodies, we have divided the body into n number of elements. N number of elements are having their own weights. If we add all the weights, finally we will get the total weight of the body itself. Now the total weight capital W will be given by W1 plus W2 plus W3 plus and so on Wn. Now as per the Varignon's theorem, see, all the weights are forces, the force by which the body is pulled towards the earth center. Therefore all the weights are parallel to one another, and W1, W2, W3 are individual forces, and the resultant of all the weights, the resultant of all the forces is the capital W. Now if you apply Varignon's theorem to these forces, the algebraic sum of the moments of individual forces about a point is equal to the moment of their resultant about the same point. Here the individual forces are W1, W2 to Wn, and the resultant of all these forces is capital W. Now take the moment about y axis. So the distance of the W, total weight W from y axis is x bar. So the moment due to resultant, about y axis is W x bar is equal to moment of individual forces about the same point, W1 x1 plus W2 x2 plus W3 x3 and so on, Wn xn. Now from this equation, x bar, the coordinate of centroid or center of gravity of the given body is x bar is equal to W1 x1 plus W2 x2 plus W3 x3 and so on, Wn xn divided by W1 plus W2 plus W3 and so on, Wn, which is nothing but the total weight capital W. This is the analytical formula for finding the center of gravity of a given body. Now similarly, Wy bar is equal to W1y1 plus W2y2 plus W3y3 and Wn yn. Y bar is equal to W1y1 plus W2y2 plus W3y3 plus and so on Wn yn divided by capital W, which is the total weight. So the y bar final equation is W1y1 plus W2y2 plus W3y3 and plus and so on Wn yn divided by sum of individual weights or total weight. Now these are the formulas for finding the center of gravity of a given body. Alternately, these equation can be written as x bar is equal to sigma I equal to n wi xi. Here the equation is wx bar is equal to wx bar is equal to algebraic sum of individual moments sigma wi xi. The equation also can be written as in the integral form. It can be written as x bar is equal to integral x dw divided by integral dw, where dw is the weight of the small body and x is the distance of the individual elements, and y bar is equal to integral y dw by integral dw. These two forms, the integral form we are going to use in the derivation of centroid or center of gravity of solids and planes. Now the expression for the coordinates of center of gravity will be given by x bar is equal to w1 x1 plus w2 x2 plus w3 x3 and so on divided by total weight w. Now by using this expression of center of gravity, we are going to find the expression or formula for finding the centroid of areas. Now this is the center of solid, center of gravity equation, because here the weight is considered, the weights are considered. Now we will reduce this equation to find the centroid of plane areas. See, we know that the weight is given by W equal to mg. Weight is given by W is equal to mg. Now replace all the weights in the equation by mg. W1 is equal to m1g, W2 is equal to m2g and W3 is equal to m3g and so on. Wn is equal to mn into g, where g is constant acceleration due to gravity. Now replace all the weights by mg. The equation is reduced to m1g x1 plus m2g x2 plus m3g x3 and so on mng xn divided by m1g plus m2g plus m3g and so on mng. Now here in this equation, the g, acceleration due to gravity, is constant and it is common in both numerator and denominator. Now take the acceleration due to gravity g common and cancel it out. The equation will become m1 x1 plus m2 x2 plus m3 x3 and so on divided by total mass. In the beginning, we have seen the center of gravity is not only the weight center, it is also the mass center. If the weight is given in the formula, we will use the equation which is having weights, and if the masses are given in the problem, we will use the mass terms m1 x1 plus m2 x2 plus m3 x3 and so on divided by total mass, sum of individual masses. Similarly, y bar m1 y1 plus m2 y2 plus m3 y3 and so on divided by total mass of the body. Right. Now the expression is now reduced into masses. Right. Now we have another relation, that is mass is equal to density into volume. Mass is equal to density rho into volume. Now in the equation, replace all mass terms m1, m2, m3 by density rho, which is a constant for the material, into volume of the individual bodies v1, v2 and v3. Right, the equation will be reduced to rho v1 into x1, where rho v1 is the term m1. m1 is replaced by rho v1. Similarly, m2 is replaced by rho v2 and m3 is replaced by rho v3. Right. Now again in this equation, the density rho of the material is same and constant in both numerator and denominator. Now take it out and cancel. The rho is taken out, taken common in both numerator and denominator, and it is cancelled. Now final equation is the x bar is equal to v1 x1 plus v2 x2 plus v3 x3 and so on divided by total volume or sum of individual volumes. See, we are going back to the definition. The center of gravity is the point at which the total mass is concentrated, and it is the point of center of volume, right. Similarly, y bar v1 y1 plus v2 y2 plus v3 y3 and so on divided by v1 plus v2 plus v3. Right. Now the expression is now reduced to volumes. The center of gravity of the solid body is given in terms of volumes. Now let us use this equation to find the center of gravity, centroid. From the equation of center of gravity, now we are going to find the equation for centroid. See, for unit thickness, for a body having unit thickness, the volume is volume into area. If the thickness is unity, the volume is equal to area into 1 or same thickness, unit thickness. Now replace the volume terms in the equation by area into thickness, and here I am considering the thickness of the body is constant throughout. Therefore T into A1, which is nothing but our V1, and T into A2, V2. Now I am replacing all the volumes by thickness into area. Now in this equation again, the thickness of the body, which is considered assumed as unit or constant in the derivation, is same in both numerator and denominator. Now take the thickness term outside, which is common in both numerator and denominator, and cancel it out. The final expression for centroid, the body which is having only areas, is a1 x1 plus a2 x2 plus a3 x3 and so on divided by a1 plus a2 plus a3 and so on an. This is the expression which is used to find the centroid of plane areas. And y bar is equal to a1 y1 plus a2 y2 plus a3 y3 and so on divided by a1 plus a2 plus a3 and so on. For the planes, the formula is x bar is equal to a1 x1 and y bar is equal to a1 y1. How many number of parts we made, that many first moments we will consider. The expressions in algebraic form: sigma I equal to 1 to n ai xi. This is a x bar, not x bar. This is for A x bar. This is for A y bar. A y bar is equal to sigma I equal to 1 to n A I y I. Now in the integral form, x bar is equal to integral x dA divided by integral dA. This integral dA is nothing but the sum of individual areas, which is equal to total area. This is in another way written as Ax bar is equal to integral x dA, where if you know the formula for total area, no need to integrate the individual areas, we can directly use the area formula. Then in that case, the equation is Ax bar is equal to integral x dA. The first moment of area, which is x into dA, the first moment of area gives us centroid, location of centroid, and y bar is also equal to integral y dA by integral dA. This integral dA is the total area, and this equation can be written as A y bar is equal to integral y dA. These two equations we are going to use to derive the centroid location for rectangle, triangle and other laminas. In this video lecture, we have covered the definition of centroid, center of gravity definition, and the expression for finding the centroid of planes is a1x1 plus a2x2 plus a3x3 and so on divided by total area, and similarly y coordinate also. And center of gravity, which is the center of weight or center of mass or center of volume, can be found by using the formulas x bar equal to w1x1 plus w2x2 plus w3x3 and so on divided by total weight. And if mass is given in the problem, these w terms, weight terms will be replaced by mass terms m1, m2, m3, and if volume is given, volume is known, we will use the volume terms in the formula. Thank you.